What if everything, every star, every galaxy, every atom in your body arose from nothing? Not empty space, but absolute nothingness. No matter, no energy, no time. And yet, here we are, inside a universe overflowing with structure, stretching for billions of light years in every direction. How can something arise from nothing? Has the universe always existed in some form? For decades, scientists have wrestled with this question, trying to assemble a coherent picture. Was our universe born from a quantum fluctuation? Did an earlier cosmos collapse, only to erupt again into a new cycle of existence? Let us explore some of the strangest and most unsettling ideas about the origin of the universe. If you think the Big Bang is the final word, think again. The reality may be far more extraordinary than you expect. The story begins with a profound shift in how we understand emptiness itself, moving from the classical idea of a void to the modern concept of a quantum vacuum. What once seemed like pure nothingness has revealed itself to be astonishingly complex. From ancient philosophy to modern physics, our view of empty space has been completely transformed. What was once imagined as featureless emptiness is now understood to be alive with activity on the smallest scales. This transformation did not happen suddenly. It emerged through centuries of observation, argument, and discovery. In ancient Greece, philosophers such as Aristotle rejected the possibility that true emptiness could exist. To him, nature abhorred a vacuum. He believed that space must always be filled with something, whether air, fire, or some unseen substance. This idea shaped scientific thinking for centuries. Even as new theories appeared, the assumption that space was filled with some form of medium remained deeply rooted. The 17th century marked a turning point. The work of Galileo, and later Newton, led to a radically new conception of space. Newton described space as an absolute void, a fixed background against which objects moved according to precise laws. In his view, space itself had no structure. It was simply the stage upon which the universe unfolded. This notion of empty space as a passive backdrop became widely accepted. Yet even in Newton's era, there were those who suspected that space might not be entirely empty after all. During the 19th century, scientists proposed the existence of an invisible substance known as the ether. This ether was thought to permeate all of space and act as the medium through which light waves traveled. Since sound required air to propagate, it seemed reasonable to assume that light also needed something to carry it. The ether fit neatly within Newtonian physics. However, in the late 1800s, a pivotal experiment altered the course of science. The Michelson-Morley experiment sought to detect the motion of the ether by observing how light moved through space. The results revealed no evidence of the ether at all. This posed a serious challenge. If space was not filled with ether, then what was it? At the turn of the 20th century, Einstein's theory of relativity offered a revolutionary perspective. Space was no longer an empty void, but a dynamic fabric capable of stretching and bending. Gravity was no longer understood as a force acting at a distance, but as the result of massive objects warping the structure of space itself. Einstein's vision moved decisively away from the idea of an inert emptiness. Even so, the true level of activity within empty space was still not fully understood. The most dramatic change came with the emergence of quantum mechanics. It revealed that even in a perfect vacuum, particles can spontaneously appear and vanish. These so-called virtual particles flicker into existence so briefly that they cannot be directly observed. This restless behavior led to the concept of the quantum vacuum. Rather than being passive, space is filled with fluctuations, tiny surges of energy occurring everywhere, all the time. This realization transformed physics. The vacuum was no longer merely the absence of matter. It became an active participant in the universe itself. Remarkably, the effects of these fluctuations can be measured. The Casimir effect, proposed in 1948, demonstrated that two closely spaced metal plates can attract one another due to the influence of the quantum vacuum. This provided direct evidence that empty space possesses real physical properties. In quantum field theory, Every type of particle is associated with a field that extends throughout space. Even when no particles are present, these fields remain, constantly fluctuating. The Higgs field, for instance, endows particles with mass. Without it, the fundamental constituents of matter would not exist in the forms we recognize. This deeper understanding of empty space reshaped cosmology itself. The discovery of dark energy, the mysterious influence driving the accelerating expansion of the universe, is closely connected to the quantum vacuum. Some physicists propose that vacuum energy arising from quantum fluctuations could be responsible for this cosmic acceleration. Yet the true nature of dark energy remains one of the greatest unsolved problems in physics. The journey from the classical void to the quantum vacuum represents one of the most profound shifts in scientific thought. What was once dismissed as nothing is now understood as a source of energy and ceaseless activity. Even today, our exploration of the quantum vacuum is far from complete, and its deepest secrets remain waiting to be uncovered. Scientists are still probing its place in the universe, asking whether vacuum energy might one day be tapped, and whether entirely new physics could be concealed within the fabric of what we call empty space. The answers to these questions continue to transform how we see the cosmos. Quantum fluctuations are the subtle spark within the void. In classical physics, a vacuum is simply the absence of matter. In quantum physics, however, even what appears to be empty space is alive with energy. That energy reveals itself through fleeting virtual particles that momentarily come into existence and then fade away. These particles do not behave like ordinary matter. They never settle into a stable state. They emerge and vanish so rapidly that we cannot observe them directly. And yet, their influence can be measured, demonstrating beyond doubt that they are real. The Big Bang, the event that set everything in motion, is often described as a colossal explosion. But what, if anything, ignited it? One possibility is that a quantum fluctuation arising from an unstable state of empty space initiated the process. On an unimaginably small scale, the universe may have begun as a minute disturbance within a quantum vacuum. Ordinarily, such fluctuations are transient, appearing and disappearing almost instantly. But under particular conditions, a fluctuation could stabilize and expand with extraordinary speed. This idea connects closely with inflation, the theory that the early universe underwent an astonishingly rapid expansion. Inflation proposes that in a tiny fraction of a second, the universe grew from something inconceivably small into something immense. If a quantum fluctuation triggered this expansion, it would suggest that the universe itself emerged from energy already present in the vacuum. Rather than beginning as a single explosive event, the cosmos may have started as a dramatic stretching of space, driven by the hidden energy of emptiness itself. If a quantum fluctuation can create one universe, might it create many? Some scientists think such events could be occurring constantly, generating innumerable universes beyond our own. This concept, known as eternal inflation, suggests that new regions of space may be continually forming within an ever-growing cosmic landscape. Even within our own universe, quantum fluctuations left an enduring imprint. As inflation stretched space, tiny variations were amplified. These minute differences in energy density later became the seeds of galaxies and stars. Without them, matter might have remained smoothly distributed, and no structure would ever have emerged. The galaxies we observe today may owe their existence to random quantum events that occurred within the first fleeting moments after the Big Bang. The notion that the universe could arise from nothing feels deeply counterintuitive. Yet experiments confirm that quantum fluctuations are real and exert measurable effects. In particle physics, they influence the behavior of fundamental forces and particles. If quantum fluctuations can shape reality on the smallest scales, it is plausible that they also played a role on the grandest scale imaginable. The vacuum itself is not merely a passive stage on which particles act. It possesses energy of its own. In some theories, this vacuum energy can shift from one state to another, producing profound changes in the universe. If an unstable vacuum state existed before the Big Bang, a quantum fluctuation might have triggered a transition that gave birth to the cosmos. If a quantum event initiated our universe, does that imply that other universes could be forming elsewhere even now? Could new universes arise in the far future? These possibilities follow naturally from the strange and beautiful rules of quantum physics. The Big Bang remains the cornerstone of modern cosmology, marking the beginning of the observable universe. But what if it was not the true beginning? For decades, physicists and cosmologists have explored the idea that the universe may have had a history before the Big Bang. Some theories propose that the cosmos undergoes endless cycles of expansion and contraction, never truly beginning and never truly ending. Others suggest that our universe emerged from a much larger pre-existing reality, perhaps through interactions involving hidden dimensions or unknown physical forces. If any of these ideas are correct, then the Big Bang was not the start of everything, but merely one chapter in a far older and grander cosmic story. One of the most widely discussed alternatives to a single beginning is the cyclic universe model. In this view, the universe follows a repeating pattern, expanding, slowing, contracting, and then beginning again. Instead of one Big Bang followed by endless expansion, the cosmos may experience an infinite sequence of Big Bangs and Big Crunches. Ancient cultures, including Hindu and Buddhist traditions, imagined the universe as moving through perpetual cycles of creation and destruction. In modern physics, similar ideas have been explored in a variety of forms. Some versions suggest that dark energy might one day reverse its effect, drawing everything back together. The universe would collapse into an extremely dense state before rebounding in another explosive expansion. Repeated endlessly, this process would imply that the universe has no true beginning or end, only continual renewal. A related concept is the Big Bounce theory. It proposes that instead of collapsing into a singularity, a previous universe reached an intensely compressed state and then rebounded, giving rise to our current expanding universe. In classical physics, gravity would eventually force everything into a single point, creating a singularity. But in quantum mechanics, effects at the smallest scales may prevent such total collapse, avoiding a singularity altogether. Some interpretations of this idea suggest that each successive universe could retain subtle imprints from the one before it, faint irregularities that might still be detectable today within the cosmic microwave background. In string theory, the most basic components of reality are not point-like particles, but minuscule vibrating strings. In one particular framework, known as the ekpyrotic model, the universe did not originate from a single explosive beginning, but from the collision of two vast higher dimensional surfaces, often referred to as branes. According to this view, space may possess more than the three dimensions we directly experience, and these higher dimensional structures could interact in dramatic ways, capable of generating entire universes. In such a scenario, the Big Bang would not be a singular, unique event, but merely one of countless collisions unfolding across an unimaginably vast cosmic landscape. Another possibility is that the universe emerged from quantum fluctuations within an eternal vacuum. If such a fluctuation occurred under precisely the right conditions, it could have initiated a period of rapid inflation, leading to the birth of our universe. This perspective implies that our universe is simply one bubble within a far larger quantum reality, a reality that continually gives rise to new universes. From this emerges the concept of the multiverse, an immense collection of universes, each possessing its own distinctive properties. Some versions of multiverse theory propose that every quantum event gives rise to a new universe, creating an endless array of parallel realities. Others suggest that different regions of space are perpetually generating new universes, separated by vast distances or even by entirely different dimensions. If this is true, then our universe would be only one among countless others, each governed by its own physical laws, matter, and possibilities. There are also theories proposing that time itself did not begin at a single moment. Instead, time may extend infinitely into the past. From this perspective, what we interpret as the Big Bang could simply represent a transition from one phase of existence to another. One way scientists explore these ideas is through mathematical modeling and careful observations of the cosmic microwave background radiation. often called the CMB. This faint afterglow from the early universe carries invaluable clues about what occurred in the earliest moments following the Big Bang. Some researchers believe that delicate patterns within this radiation might reveal evidence of a universe that existed before our own. Discovering traces of an earlier cosmic phase would represent a profound breakthrough in our understanding of cosmic history. Yet because the laws of physics as we know them break down under the extreme conditions of the early universe, obtaining direct evidence of anything preceding the Big Bang remains extraordinarily challenging. Many of these ideas, while grounded in robust theoretical frameworks, remain speculative because they cannot yet be tested. Still, advances in physics and technology may eventually provide new insights. As scientists develop ever more sensitive instruments and probe deeper questions about space, time, and matter, they may uncover clues pointing to a time before the Big Bang. Quantum gravity plays a crucial role in this quest to understand cosmic origins. The universe appears to operate under two distinct sets of rules that seem fundamentally incompatible. One governs the behavior of planets, stars, and galaxies, following the familiar laws of gravity, first articulated by Isaac Newton and later refined by Albert Einstein. The other governs the strange realm of the very small, atoms, particles, and the energy fields that surround them, described by quantum mechanics. Both frameworks have been confirmed repeatedly through experiment, yet they resist being combined into a single coherent theory. This poses a serious problem because to fully understand the birth of the universe, gravity and quantum mechanics must be considered together. At the moment of the Big Bang, the entire universe was compressed into an unimaginably small region. Under such conditions, gravity would have been acting at the quantum scale, where the principles of quantum mechanics dominate. However, Einstein's theory of general relativity, which so successfully describes gravity on large scales, fails at the quantum level. In contrast, quantum mechanics, which governs the microscopic world, does not incorporate gravity at all. When these two theories are brought together, they break down, leaving physicists without a complete description of the universe's earliest moments. To truly understand cosmic origins, scientists must develop a unified framework that merges these two fundamental pillars of physics. One promising avenue is the search for a theory of quantum gravity, an explanation of how gravity behaves in the quantum realm. This remains one of the greatest unsolved challenges in physics. If such a theory can be established, it may illuminate what occurred in the very first instant of the universe, and perhaps even what existed before the Big Bang. Among the leading candidates is string theory. Rather than viewing particles as dimensionless points, string theory proposes that all entities are composed of tiny vibrating strings. These strings are so extraordinarily small that even the most powerful conceivable microscope could never observe them directly. The way each string vibrates determines the particle or force it represents, including gravity. In this framework, gravity is not a separate force, but a natural outcome of how these strings interact with the fabric of space. String theory also suggests that space itself may include more than 3 dimensions. While we experience height, width, and depth in everyday life, additional dimensions could exist beyond our perception. If this is correct, the early universe may have behaved in ways very different from our current expectations. These hidden dimensions could have influenced how space expanded after the Big Bang, or even played a fundamental role in the universe coming into existence at all. An alternative approach to quantum gravity is loop quantum gravity. Instead of treating space as a smooth, continuous backdrop, this theory proposes that space itself is composed of tiny, indivisible units, similar to pixels on a screen. These discrete units of space form a structure that could prevent the universe from collapsing into a singularity. Such a mechanism might explain how the universe transitioned from an earlier state into the one we observe today. Some versions of loop quantum gravity even suggest that time behaves very differently at the quantum level. Rather than flowing smoothly, time may emerge from deeper interactions within the fabric of space itself. This opens the possibility that time existed before the Big Bang, allowing for a cosmic history that stretches back beyond what we currently perceive as the beginning. We now encounter a third idea, one that arises from the holographic principle. This notion proposes that the entire universe could be understood as a three-dimensional projection of information encoded on a distant surface with fewer dimensions. From this perspective, the deepest layer of reality is not constructed from matter or energy in the conventional sense, but from information itself. If the holographic principle turns out to be correct, then the origin of the universe may not have been a conventional explosion. Instead, it could have been the gradual unfolding of information that gave rise to space and time. One of the greatest difficulties in building a theory of quantum gravity lies in testing it. Unlike other branches of physics, where experiments can be carried out in laboratories or observations made with telescopes, probing quantum gravity directly would demand recreating the extreme conditions of the very early universe, with current technology that is simply beyond our reach. As a result, physicists are forced to search for indirect evidence, faint signatures such as subtle patterns in the cosmic microwave background, the behavior of black holes, or unexpected effects in high-energy particle experiments. In several respects, black holes resemble the conditions that prevailed in the early universe. Stephen Hawking famously predicted that black holes are not entirely black, but instead lose energy very slowly through a process now known as Hawking radiation. This occurs because quantum effects near the edge of a black hole allow particles to briefly appear and then escape. If quantum gravity plays a role in black holes, then studying how they evaporate might offer clues about the universe in its earliest moments. The cosmic microwave background also preserves information from the infant universe, and tiny irregularities within it could reveal whether quantum gravity influenced the first fractions of a second after the beginning. If patterns are found that cannot be explained by standard cosmology, they may point toward new physics that goes beyond Einstein's equations. There is also a deeper question to consider: whether the universe required a beginning at all. Some approaches to quantum gravity suggest that time itself behaves very differently under extreme conditions. If space and time emerge from quantum interactions, then the Big Bang may not have been a singular event, but a transition from one state to another. The universe might have existed forever in some form, with no absolute beginning, only continual changes in structure over time. Should scientists succeed in unifying quantum mechanics and gravity into a single framework, it would transform the way we think about space, time, and the architecture of the universe. Such a breakthrough could even lay the groundwork for entirely new technologies or discoveries. Scientists continue to push forward, driven by a desire to understand the most fundamental nature of everything that exists. The emergence of space-time, the moment when geometry itself is born, may have occurred before the universe as we recognize it today. Prior to that, there may have been no space and no time, at least not in any familiar sense. The fabric of reality might not be fundamental at all, but instead something that arises from deeper processes that bear little resemblance to space, stretching endlessly, or time flowing smoothly in one direction. One helpful way to think about this is to compare space-time with temperature. Temperature feels like a basic property of the world, yet in truth, it is simply a measure of the collective motion of microscopic particles. If you zoom in far enough, down to individual atoms, the concept of temperature vanishes. It does not exist independently, but emerges from the interactions of many smaller components. Some physicists suspect that space and time behave in a similar way. At the smallest scales, they may not exist at all, only appearing when enough interactions occur to give them meaning. In the quantum world, particles do not always occupy precise locations. Their positions can be uncertain, and they may even exist in multiple states simultaneously. If space itself is something that emerges, then at the smallest scales locations may not be well defined. Reality could be built from networks of relationships, with space forming only when enough of these connections become stable. Certain theories propose that the fundamental structure of reality is not based on space at all, but on networks of information. In these views, space is not a physical substance, but a way of organizing relationships among tiny building blocks. At large scales, these networks behave in a way that gives rise to the smooth geometry of space that we experience. Just as countless grains of sand can come together to form a solid beach, individual units of information could collectively create the structure of space-time. One model, inspired by this idea, is known as causal set theory. In this approach, space-time is not a continuous fabric, but a collection of discrete elements, like points connected through cause and effect. Rather than existing as a background, space-time is constructed from these relationships, appearing smooth only when viewed at large scales. If causal set theory is correct, then at the smallest levels space does not exist as an empty container, but emerges only when sufficient interactions take place. Another approach comes from loop quantum gravity. In the same way that energy appears in discrete packets, space itself may be divided into tiny, indivisible units, known as loops. These loops form a kind of hidden network beneath the structure of space-time at the smallest scales. Space may be woven together like a fabric made from interlocking loops, and if that is true, it would imply that space itself possesses a smallest possible unit, beyond which the very idea of distance loses its meaning. If space is built from fundamental units, then time may be structured in a similar way. Some physicists suggest that time is not a smooth, continuous flow, but instead unfolds as a sequence of discrete moments, rather like individual frames in a film. At the quantum level, there may exist a fundamental tick of time. This notion is supported by certain interpretations of quantum mechanics, which propose that time emerges from changes in quantum states, rather than existing as an independent backdrop to events. One of the most profound implications of these ideas is that the Big Bang may not have marked the absolute beginning of space and time, but instead the moment when they emerged from something deeper and more fundamental. If space-time itself had to form, then there may have been a phase before the Big Bang in which space did not exist in any recognizable form. Rather than a single explosive origin, the universe may have transitioned from a timeless quantum state into the dynamic, expanding cosmos we observe today. Scientists are searching for evidence of these possibilities in a number of ways. If space arose from deeper processes, subtle traces of that origin might still be imprinted in the oldest light in the universe. The extreme warping of space and time around black holes could also reveal how space-time behaves when pushed to its absolute limits. If space-time is something that emerges rather than something fundamental, then what lies beyond space-time itself? What deeper principles shape its structure? And if space and time are not fundamental, what does that imply for our understanding of existence? Multiverse ideas introduce the possibility of multiple beginnings from nothing. The cosmos, rather than being a single expanding bubble, could be a vast multiverse filled with countless distinct regions, each with its own laws, structures, and origins. If this is the case, then instead of asking how everything began, we may need to ask how many different ways something can emerge from what we call nothing. According to the idea of eternal inflation, space itself is expanding at an extraordinary rate in most regions, but in certain pockets this rapid expansion slows. These calmer regions become bubble universes, each forming with its own unique properties. Our universe could be one such bubble, surrounded by an endless cosmic foam of other universes. If eternal inflation is correct, then new universes could be forming continually. The process never truly ends. Each bubble universe emerges from a quantum fluctuation, a random shift of energy within the vacuum of space. This suggests that instead of a single Big Bang, the cosmos may be filled with countless Big Bangs, each giving rise to a separate universe. Some of these universes might share physical laws similar to our own, while others could be entirely unfamiliar, governed by rules of physics that make them strange and alien to us. In string theory, the way fundamental strings vibrate determines the properties of a universe, its particles, forces, and dimensions. Yet the theory predicts an enormous number of possible ways these strings can be arranged. Some estimates suggest there could be around 10 to the power of 500 possible configurations, each corresponding to a different universe with different physical properties. In certain versions of the multiverse, universes can even branch from one another. The many worlds interpretation of quantum mechanics proposes that every quantum event, every tiny random change in the state of a particle, could cause the universe to split. If this picture is correct, then an uncountable number of parallel universes may exist, each representing a different version of reality. Every decision, every movement of an atom could lead to a separate world in which events unfold in a different way. If black holes act as gateways to new regions of space, then each black hole in our universe could potentially give rise to a new universe beyond its event horizon. In that case, our own universe may have formed from the remnants of a previous one, continuing an endless cycle of cosmic creation. While the multiverse remains a highly speculative idea, scientists continue to search for ways to test it. Some look for evidence in the cosmic microwave background, while others search for signs of extra dimensions or subtle variations in fundamental constants that could point toward a deeper underlying reality. Vacuum energy and the sea of possibility arise from the fundamental nature of quantum fields. Even in a region of space containing no particles, these fields are never completely still. They continue to vibrate at a fundamental level, producing brief bursts of energy that appear and vanish almost instantly. Under normal conditions, these fluctuations are tiny, too fleeting to have any noticeable effect, but under the right circumstances they could play a far greater role, potentially giving rise to entire universes. The idea of vacuum energy is also connected to one of the great puzzles of physics, the cosmological constant. When the equations of general relativity were first formulated, a term was included to represent the energy of empty space. At the time, it was seen as a mathematical adjustment, but later discoveries revealed that vacuum energy is real and that it has a measurable influence on the evolution of the universe today. The cosmological constant is closely tied to what we call dark energy. When we attempt to calculate the amount of energy contained within empty space, the result we observe is astonishingly small compared with what our theories predict. If calculations derived from quantum field theory were entirely correct, the energy of the vacuum should be so immense that it would rip galaxies apart almost instantaneously. Instead, what we measure is vastly weaker. This discrepancy suggests that we are either missing a crucial element of the underlying physics, or that there exists some unknown process delicately balancing vacuum energy at precisely the level required for our universe to exist at all. If vacuum energy is involved in the creation of new universes, then different regions of a multiverse could possess different values of this energy. Some universes might contain a far stronger vacuum energy, causing space to expand so rapidly that stars and galaxies never have the chance to form. Others might contain almost no vacuum energy at all, resulting in a universe that collapses in on itself shortly after it begins. The fact that our universe has a level of vacuum energy compatible with life may hint at the existence of many universes, each governed by different physical properties. If space itself carries energy, then in principle it might be possible to extract or modify that energy. This idea appears in speculative discussions of advanced propulsion systems, where manipulating vacuum energy could one day permit travel faster than the speed of light. Although this remains purely theoretical, the notion of tapping into the energy of empty space continues to capture scientific imagination. The influence of this energy is evident in experiments such as the Casimir effect, which demonstrates that vacuum energy is not merely an abstract concept but something capable of affecting physical objects in measurable ways. If vacuum energy truly drives cosmic creation, then the birth of universes may not require any external cause. Instead, the natural fluctuations of the vacuum itself could be sufficient to spark the formation of entire cosmic structures. Entropy presents another profound puzzle. It is a fundamental aspect of how the universe behaves, a measure of disorder, and according to the second law of thermodynamics, entropy always increases with time. Left undisturbed, systems evolve from order toward disorder. A shattered glass does not reassemble itself, and a drop of ink in water disperses rather than gathering back into a single point. Yet when we observe the early universe, we encounter something deeply unexpected. It began in a state of extraordinarily low entropy, highly ordered compared with everything that followed. If entropy naturally increases, why was the universe so ordered at the start? When the universe first emerged from the Big Bang, it existed in a hot, dense state in which matter and energy were distributed almost perfectly evenly, with only minute variations. At first glance, this appears simple and chaotic, but in terms of entropy, it was remarkably low. As time passed, the universe expanded and cooled, allowing complex structures to form. Galaxies, stars, and planets emerged, only to eventually break down again as everything drifts toward a condition of maximum entropy, where matter and energy are spread so uniformly that no useful work can be done. This final condition, often called the heat death of the universe, represents ultimate disorder. The mystery lies in why the universe began in a state that allowed such structure to arise. If high entropy is the natural endpoint, why did the universe not begin that way? Why was there order that gave rise to stars and galaxies instead of an immediate descent into randomness? One way to approach this question is to consider gravity. In most systems, increasing entropy means becoming more spread out, but gravity behaves in a counterintuitive way. When a cloud of gas collapses to form a star, it appears to become more ordered rather than less. This happens because gravity draws matter together into dense structures, yet in doing so, it increases the total entropy of the universe by releasing heat and radiation. Structure formation does not reduce entropy, it redistributes it. Some physicists suggest that the universe's initial state was not only low in entropy, but also extraordinarily specific. For space and time to emerge as we experience them, the initial conditions had to be precisely right, almost as though the universe began in a finely tuned state. This idea is often called the past hypothesis, the proposal that the early universe existed in a unique condition that set everything else in motion. While cosmic inflation explains why the universe looks so uniform on the largest scales, it does not fully explain why entropy started out so low. The deeper question remains, why did inflation occur at all, and why were its initial conditions so special? In cyclic models of the universe, the Big Bang is not the beginning but one phase in a much longer story. If the universe collapses and then expands again, the conditions at each new beginning might be reset in a way that keeps entropy low. Yet this raises further challenges, particularly the question of how entropy could be reset with each cycle rather than accumulating endlessly. If a multiverse exists, then perhaps we inhabit a universe that simply happened to begin with low entropy. In that case, our universe is one possibility among many, and we observe a low entropy beginning only because we exist in a universe where conditions allowed complex structures, including life, to form. Had our universe begun with high entropy, it may have been too chaotic for stars and planets to develop, and observers like us would not be here to ask these questions. This entropy paradox is not solely about the past. It also shapes how we think about the future. As entropy continues to rise, the universe will eventually reach a state in which no further work is possible. Stars will burn out, black holes will evaporate, and matter will be evenly dispersed throughout an ever-expanding void. Yet if the universe can begin anew, or if new regions of space can emerge from vacuum fluctuations, then entropy may not be the final chapter. Instead, the cycle of order and disorder could persist, driven by processes even more fundamental than those we currently understand. Revisiting cosmic inflation beyond the standard picture, the rapid expansion associated with inflation smoothed out irregularities, shaping the universe into what we observe today. The theory explains why the cosmos appears uniform in every direction and why distant regions of space share similar properties, despite never having been in direct contact with one another. Inflation also offers an explanation for why certain predicted defects are absent from the fabric of space-time. Early versions of the Big Bang suggested that relics such as magnetic monopoles, hypothetical particles possessing only a single magnetic pole, should be widespread throughout the cosmos, yet none have ever been observed. Inflation resolves this puzzle by proposing that space expanded so dramatically that any such relics would have been diluted to extreme rarity or carried far beyond the limits of what we can observe. Achievements like these have helped establish inflation as a central element of modern cosmology, but the idea is not free from difficulty. One of its most profound challenges is that inflation depends on an unknown force. The sudden expansion is believed to have been driven by a mysterious entity, often referred to as the inflaton field, which has no confirmed counterpart within the standard model of particle physics. We do not yet know what this field truly was or what form of energy it contained. Although many theoretical models suggest possible origins, there is no direct evidence revealing the true nature of the inflaton. As a result, inflation is a framework that explains observations remarkably well, yet lacks a clearly established physical foundation. Another unresolved issue concerns how inflation came to an end. According to the theory, the inflaton field eventually decayed, transferring its energy into the particles and radiation that later formed the universe we see today. However, the precise mechanism behind this transition remains uncertain. Some models describe a gentle conclusion to inflation, while others suggest it may have ended in violent releases of energy, producing regions of high density that went on to shape later cosmic structure. These uncertainties have inspired alternative ideas, including eternal inflation and bouncing universe models, which extend beyond the standard picture. There are also proposals that focus on altering gravity itself. In some theories, what we interpret as inflation could emerge from an unfamiliar aspect of gravity that becomes relevant only at extremely high energies. In this view, space-time in the earliest moments may have behaved differently, naturally evolving toward a smooth and uniform state without the need for an additional field like the inflaton. If this is correct, inflation may simply approximate a deeper and more fundamental process. Within certain versions of string theory, inflation could be driven by interactions involving extraspatial dimensions predicted by the theory but too small to detect directly. If these hidden dimensions influence the early universe, they might offer an entirely new account of how inflation occurred, or even suggest that a different mechanism replaced it altogether. Observations are essential for distinguishing between these competing ideas. One of the strongest pieces of support for inflation comes from the cosmic background radiation. Tiny variations within this radiation reveal patterns that align with inflationary predictions. Yet different models of inflation, and even some alternatives, can generate similar patterns, making it difficult to identify the correct explanation. Scientists therefore seek additional evidence that could confirm or challenge inflation more decisively. A major objective is the detection of primordial gravitational waves, subtle ripples in space-time that may have been produced during inflation. If discovered, they would provide compelling support for a phase of rapid expansion. Experiments using highly sensitive telescopes to examine the polarization of the cosmic background radiation are actively searching for these signals. A confirmed detection would not only reinforce the case for inflation, but also help determine which version of the theory most closely reflects reality. Another strategy involves searching for large-scale irregularities. Although inflation is expected to smooth the universe, certain variations could still exist depending on the precise details of how it unfolded. Finding such features could offer clues about the nature of the inflaton field, or even indicate that inflation operated differently than we currently imagine. Closely tied to these questions is the problem of singularities. A singularity represents a point of infinite density, where space and time appear to cease functioning. This concept arises in two key areas of physics, at the cores of black holes and at the very beginning of the universe. Tracing cosmic expansion backward leads to a state in which all matter and energy converge into a single point of infinite density. Yet infinities in physics signal a breakdown in understanding. They imply that our theories are incomplete, that essential elements are missing from our equations. For decades, physicists have sought ways to address this by developing new mathematical approaches that reinterpret singularities in a more coherent manner. If our best description of gravity, Einstein's general relativity, leads inevitably to infinities, then a new framework is required. One approach modifies the equations of general relativity itself. Some models introduce additional terms that prevent singularities from forming, acting as corrections that become important when quantum effects are taken into account. Through this route, researchers aim to describe the birth of the universe without invoking an impossible state of infinite density. Another technique explores alternative geometries. In standard cosmology, space-time follows a specific geometric structure, but near a singularity, this geometry may change, obeying different mathematical rules. If space-time behaves differently at extremely high energies, the notion of an infinite singularity may no longer be necessary. Instead, the beginning of the universe could be understood as a transition between distinct geometric phases. This idea draws inspiration from topology, a branch of mathematics concerned with properties of space that remain unchanged under continuous transformations. By applying these topological methods, physicists hope to gain a clearer and more accurate picture of the universe's earliest moments. Another avenue of thought draws on the language of complex numbers and higher dimensional spaces. In conventional physics, time is treated as a real quantity, progressing steadily in a single direction from past to future. Yet some researchers suggest that near a singularity, time itself may behave in a fundamentally different way. Rather than collapsing into meaninglessness, time could adopt an alternative mathematical form that prevents infinite density from ever arising. By reformulating the equations of cosmology to include extra dimensions or complex variables, physicists are opening new ways of describing the universe at its very beginning. Some argue that singularities may not exist at all in physical reality, but instead emerge from the limits of our current understanding of gravity. Throughout physics, infinities tend to appear precisely where our theories fail, only to vanish once a deeper framework is found. Early theories of electromagnetism, for instance, were riddled with infinities that later disappeared with the development of quantum field theory. In the same way, cosmological singularities may signal not a true feature of the universe, but an incomplete description of gravity. If so, a future theory of quantum gravity might remove singularities entirely, replacing them with a smooth and continuous account of the universe's earliest moments. Testing such ideas remains one of the greatest challenges in modern physics. Conditions near a singularity cannot be recreated in any laboratory, and direct evidence is limited to the faint information carried by cosmic radiation. Still, future observations and experiments may offer indirect clues that support or challenge these models. Primordial black holes, relics from the earliest cosmos. In the first instance, after the Big Bang, the universe was extraordinarily hot and dense, filled with rapidly expanding energy and matter. Even then, tiny variations in density existed, destined to become the seeds of galaxies. In regions where matter was concentrated enough, gravity may have been strong enough to crush them into black holes almost immediately. These would be primordial black holes, formed not from dying stars, but from the turbulent conditions present at the birth of the universe itself. Unlike ordinary black holes, which emerge millions or billions of years later, primordial black holes would have existed from the very beginning. Their masses could span an enormous range, from extremely small microscopic objects to vast black holes many times more massive than the Sunday. The smallest among them may have evaporated over time through Hawking radiation, while larger ones could still persist today, scattered throughout the universe, and influencing the formation of galaxies, stars, and the large-scale structure of the cosmos. If primordial black holes exist, they could help explain several long-standing cosmic mysteries. One possibility is that they contribute to dark matter, the unseen substance that accounts for most of the universe's mass, yet has never been directly detected. The dominant view holds that dark matter consists of unknown particles, perhaps weakly interacting massive particles or axions. However, decades of experiments have failed to reveal such particles, and observations have yet to pin down their properties. Because black holes emit no light, they could be hiding in plain sight, shaping the motion of galaxies and clusters through gravity alone. Some researchers suggest that a population of ancient, small black holes could account for at least part of the missing mass. Black holes respond to gravity in exactly the same way as dark matter, potentially explaining the extra-gravitational effects observed in galaxies without invoking new particles. If distributed throughout space, they would generate the same invisible mass currently attributed to dark matter. There are, however, significant challenges to this idea. Black holes are not completely dark. Although they emit no light directly, they can interact with ordinary matter in observable ways. Even small black holes can draw in gas and dust through accretion. As matter spirals inward, it heats up and releases radiation. If large numbers of primordial black holes existed, they might have produced too much radiation in the early universe, altering the cosmic microwave background. Measurements of this background place strong limits on how many primordial black holes could exist without conflicting with known data. Some models still allow them to contribute to dark matter, particularly if they span a range of masses or behave in unexpected ways. If they cluster together rather than being evenly spread, their signatures might be harder to detect. Others propose that dark matter could consist of black hole remnants, objects left behind after tiny primordial black holes evaporated through Hawking radiation. There is also the mystery of supermassive black holes, the colossal objects residing at the centers of galaxies, including our own Milky Way. These giants contain millions or even billions of times the mass of the Sun, yet how they formed so early in cosmic history remains unclear. One possibility is that primordial black holes acted as the initial seeds. If some were slightly larger than others, they could have grown rapidly by merging with nearby matter, eventually becoming the massive black holes we observe today. Rather than forming from collapsing stars, the first black holes may have been present from the very start. Because they emit no light, primordial black holes can only be detected through their gravitational influence. One method involves gravitational lensing, where massive objects bend and magnify the light from distant stars. If a primordial black hole passed in front of a star, it could briefly cause the star to brighten. By carefully monitoring such events, astronomers may be able to determine whether tiny, ancient black holes are scattered across the cosmos. Another approach searches for signs of their evaporation. Some primordial black holes may still be disappearing today, releasing brief flashes of high-energy radiation as they vanish. Satellites and observatories, designed to detect gamma rays, could capture the final signals of these elusive objects. As they gradually evaporate in certain theoretical frameworks, these ancient objects may display remarkable characteristics, behaving in ways unlike the black holes born from the collapse of massive stars. They could harbor exotic forms of matter, or perhaps even maintain connections to distant regions of the universe through hypothetical constructs such as wormholes. Some models propose that their existence may have influenced the birth of the very first stars and galaxies, subtly reshaping how matter was distributed throughout the cosmos. If primordial black holes once existed in large numbers, their gravitational influence could have sculpted the universe on both small and vast scales, leaving traces that scientists might still uncover today. One of the most profound questions surrounding primordial black holes is whether they truly formed at all. Although the concept is deeply compelling, no direct observation has yet confirmed their presence. A wide range of experiments and astronomical observations have instead placed strict limits on how abundant these objects could be within the universe. Were they too common, their impact would be unmistakable, yet if they are exceedingly rare, detecting them becomes an extraordinary challenge. The ongoing search for primordial black holes is part of a broader attempt to understand the earliest moments of cosmic history. If they exist, these objects could form a crucial bridge between the physics of the Big Bang and the black holes we observe scattered across the universe today. The structure of the universe we see now is far from random. Galaxies, clusters, and immense filaments are arranged in a delicate and interconnected pattern, stretching across enormous cosmic distances, a vast architecture known as the cosmic web. This grand design traces its origins back to the very beginning of time. Subtle imprints preserved in the cosmic microwave background revealed minute variations in density, fluctuations that would eventually grow into the galaxies and clusters that populate the universe today. Conventional models explain this growth as the result of quantum fluctuations stretched to cosmic scales during inflation. Yet some theories suggest that primordial black holes may have played a significant role in shaping this structure. If such black holes were present in meaningful numbers, they could have influenced how matter gathered together in the early universe. Ordinarily, slight differences in density allowed gravity to slowly draw gas inward, leading to the formation of the first stars and galaxies over hundreds of millions of years. The presence of primordial black holes, however, would have created additional gravitational wells, potentially accelerating this entire process. Rather than waiting for tiny fluctuations to amplify on their own, These black holes could have acted as seeds, pulling in gas and enabling structure to emerge more rapidly. In certain models, these early black holes may have merged over time, giving rise to the supermassive black holes that now sit at the centers of galaxies. The origin of these colossal objects remains one of astronomy's enduring mysteries. While the standard view holds that they grew gradually from smaller black holes, primordial black holes offer a striking alternative, suggesting that some central black holes may have existed since the earliest epochs, bypassing the slow path of growth altogether. Their gravitational influence could also have shaped the cosmic web itself. As matter collapsed along invisible filaments of dark matter, galaxies formed where these filaments intersected. If primordial black holes were embedded within this early environment, their gravity might have strengthened certain filaments while inhibiting the accumulation of matter in others, subtly modifying how the cosmic web evolved. The LIGO and Virgo observatories have detected ripples in space-time produced by the collision of black holes billions of light-years away. Some researchers speculate that a fraction of these merging black holes could be primordial in origin rather than remnants of massive stars. Should future observations uncover black holes with unusual characteristics, such as masses that do not align with standard stellar evolution, this could offer indirect evidence for the existence of primordial black holes. The search continues, and future discoveries may ultimately reveal whether these elusive objects were the hidden architects of the cosmos. The cosmic microwave background is often described as the universe's oldest light, a relic archive carrying a snapshot of the cosmos as it was nearly 14 billion years ago. Although this ancient radiation appears almost perfectly uniform, faint variations in temperature and density encode the story of how galaxies and large-scale structures eventually formed. These fluctuations are largely consistent with predictions from the standard model of cosmology. Yet certain features, known as anomalies, resist simple explanation. One of the most famous of these is the cold spot, a region in the southern sky where the radiation is cooler than expected. First identified by the Wilkinson Microwave Anisotropy Probe and later confirmed by the Planck satellite, this area is both larger and colder than typical fluctuations elsewhere in the cosmic microwave background. Some scientists argue that the cold spot could simply be a rare statistical fluke, an unusually large but random variation. Others, however, believe it may point to something far more intriguing. One possibility is that the cold spot is associated with an enormous structure called a supervoid, a vast region of space containing far fewer galaxies and much less matter than its surroundings. If such a supervoid lies along the line of sight between Earth and the cold spot, it could have influenced the journey of cosmic microwave background photons. Through a process known as the integrated Sachs-Wolf effect, light traveling through a region of lower density can lose energy as space expands. While some studies have found evidence for a supervoid in this direction, it does not appear large enough to fully account for the anomaly, leaving open the door to other explanations. A more speculative idea suggests that the cold spot could be evidence of a collision between our universe and another bubble universe within a much larger multiverse. If our cosmos is just one of many emerging within an immense cosmic landscape, interactions between these regions could leave behind subtle but detectable signatures imprinted in the oldest light of all. Some theorists have put forward the idea that, at some moment deep in the past, our universe may have collided with another universe, and that such an encounter could have subtly reshaped the temperature pattern of the cosmic microwave background in certain regions, potentially offering an explanation for the mysterious cold spot. Another equally perplexing feature is what has come to be known as the axis of evil, a phrase used to describe an unexpected alignment of temperature variations stretching across vast areas of the sky. According to the standard picture of cosmology, fluctuations in the cosmic microwave background should be randomly distributed on all scales. Yet observations from the Wilkinson Microwave Anisotropy Probe and the Planck mission reveal that the largest scale variations appear to line up along a specific direction rather than pointing randomly across the sky. This kind of alignment is deeply difficult to reconcile with conventional physics. One possible explanation is that this apparent alignment is an illusion caused by our particular location in the universe. Some scientists have suggested that if our local cosmic environment is not perfectly uniform, it could bias the way we observe the cosmic microwave background, creating the impression of a preferred direction. However, no convincing mechanism has been identified that could generate such a large-scale effect without conflicting with other precise observations. Another possibility is more radical. The alignment may be telling us that the universe itself possesses a preferred direction, an intrinsic anisotropy on the largest scales. If this were true, it would undermine one of the foundational assumptions of modern cosmology, namely that the universe looks the same in every direction when viewed on sufficiently large scales. Certain theoretical models suggest that a preferred direction could have been imprinted at the birth of the universe, perhaps linked to the way space-time expanded during the period of inflation. If so, this alignment could offer a glimpse into the physical processes that governed the universe in its very earliest moments. Beyond these specific anomalies, there are other unexpected features in the cosmic microwave background that continue to intrigue researchers. Some studies indicate that the statistical properties of the background differ between opposite halves of the sky, an asymmetry that sits uneasily within the standard cosmological model. Other investigations explore whether faint signatures might have been left behind by exotic cosmic structures, such as cosmic strings, hypothetical defects in space-time that may have formed shortly after the Big Bang. Studying these anomalies is extraordinarily challenging because the cosmic microwave background is incredibly faint, and even tiny errors in measurement or analysis can introduce patterns that are not truly there. For this reason, scientists are meticulous in refining their observations, relying on independent data sets and sophisticated statistical methods to confirm that any detected anomalies are genuine. The Planck satellite, for instance, produced the most precise maps of the cosmic microwave background ever made, confirming many earlier results while also raising new and deeper questions. Future missions, including proposals such as the Probe of Inflation and Cosmic Origins satellite, aim to deliver even more detailed observations that may help resolve these puzzles. Whether these strange patterns are mere statistical flukes, artifacts of observation, or hints of new physics, each discovery brings us closer to understanding the deeper mysteries of the cosmos. Polarization patterns open another window onto hidden information in the cosmic microwave background. While temperature variations have already taught us a great deal about the structure of the early universe, polarization provides an even more subtle and revealing layer of insight. The polarization patterns embedded in the cosmic microwave background may hold answers to some of the most profound questions in cosmology, including how the universe evolved, whether inflation truly occurred, and what forces shaped the very fabric of space-time. Light is said to be polarized when its waves vibrate preferentially in a particular direction. On Earth, polarization is familiar from reflections off surfaces such as water or glass, where light becomes aligned in a specific orientation. In a similar way, the polarization of the cosmic microwave background was imprinted long ago, at the moment when the first atoms formed and photons were finally able to travel freely through space without constant scattering by free electrons. This transition, known as recombination, left behind delicate polarization signatures that were frozen into the radiation as the universe continued to expand. There are two principal forms of polarization in the cosmic microwave background, known as E mode and B mode. E mode polarization is relatively easier to detect and was first observed in the early years of the 21st century. It arises naturally from density variations in the young universe and reveals how matter was distributed at the time the cosmic microwave background was released. These E modes complement and refine the information gained from temperature measurements, offering a more complete portrait of the universe in its infancy. B mode polarization, by contrast, is far more elusive, yet it carries even deeper implications. It is thought to be produced through two mechanisms, one involving gravitational lensing and the other arising from primordial gravitational waves. The second of these is especially significant because it could provide direct evidence for cosmic inflation. If inflation did occur, it would have stretched tiny quantum fluctuations to cosmic scales, leaving behind a distinctive B-mode polarization pattern in the cosmic microwave background. Detecting this signal would represent one of the most powerful confirmations of inflation and a monumental advance in cosmology. In 2014, the BICEP 2 experiment at the South Pole captured worldwide attention by announcing the detection of B-mode polarization that might be linked to primordial gravitational waves. The excitement was immense, as this would have constituted the first direct evidence for inflation. However, subsequent analyses showed that much of the signal could be explained by dust within our own galaxy, which can polarize light in a way that closely resembles the expected B-mode pattern. Although this result was disappointing, it did not end the search. New experiments are now being designed with the precision needed to disentangle genuine cosmological signals from foreground contamination. Beyond inflation, studies of cosmic microwave background polarization also shed light on the large-scale structure of the universe. As cosmic microwave background photons journey across the cosmos, their paths are subtly deflected by the gravitational influence of massive structures, a phenomenon known as weak gravitational lensing. This process slightly alters the polarization patterns, generating an additional source of B-modes. By carefully mapping these distortions, scientists can reconstruct the distribution of both visible matter and dark matter throughout cosmic history. This approach provides an independent and powerful method for studying dark matter itself. Dark energy may also leave its mark on polarization patterns, as changes in the expansion rate of the universe influence how gravitational lensing affects the cosmic microwave background, offering yet another tool for probing this mysterious force. Although dark energy remains one of the greatest enigmas in cosmology, increasingly precise polarization measurements may help reveal how it has evolved over time. The future of cosmic microwave background polarization research lies in achieving even greater precision. The upcoming LIGHTBIRD satellite, led by the Japan Aerospace Exploration Agency, has been specifically designed to target primordial B-modes with unprecedented sensitivity. By observing the sky from space, largely free from atmospheric interference, LIGHTBIRD aims to detect the faint signature of inflationary gravitational waves, if they exist at all. At the same time, next-generation ground-based observatories will continue to push observational limits. The search for primordial B-modes is ultimately a quest to understand the nature of space-time itself, to explore the role of gravity in the earliest moments of the universe, and to uncover clues about the fundamental laws that govern reality. The cosmic microwave background, often spoken of as a fossil light from the dawn of time, carries within it clues that we are only just beginning to read. Its patterns of polarization, extraordinarily faint and challenging to observe, may ultimately reveal some of the deepest truths about how the universe began and how it evolved. Among the most important features scientists study are the temperature fluctuations imprinted across this ancient radiation. With new data have come unexpected trends. One of the central ideas is how these temperature variations are distributed across different scales. In theory, there should be a precise balance between fluctuations on very large scales and those on much smaller ones, with the finer variations becoming more prominent as we examine the picture in greater detail. This behavior follows predictions made by inflationary models, in which tiny quantum fluctuations were stretched to cosmic proportions during a brief but dramatic period of rapid expansion in the universe's earliest moments. Yet, recent analyses of data from the Planck mission suggest something intriguing. The temperature variations on the larger scales appear weaker than theory anticipates. The amount of power at these scales is slightly lower than predicted, opening the possibility that inflation may not have unfolded exactly as our simplest models assume. One particularly striking anomaly is the apparent lack of temperature variation across the very largest distances. According to the Standard Model, fluctuations should exist even on these immense cosmic scales, but observations show them to be surprisingly subdued. This raises the possibility that conditions in the very early universe limited how large such variations could grow. Some researchers have suggested this might hint that inflation lasted for a finite period, rather than continuing indefinitely, as certain models propose. Others have explored a more radical idea, that our universe might be connected to a larger structure, with physics beyond our observable cosmos subtly shaping its earliest development. More recent studies have turned their attention to where new physics might be concealed within the fine structure of these temperature patterns. One avenue of investigation considers whether exotic particles present in the early universe influenced the formation of these fluctuations. If unknown forms of dark matter or additional species of neutrinos existed, they could have left delicate imprints in the cosmic microwave background, slightly modifying the expected distribution of temperatures. Some theoretical models propose that interactions between dark matter and ordinary matter in the early universe may have damped certain fluctuations, producing small departures from standard predictions. Detecting such minute effects demands extraordinary precision. Scientists must carefully account for numerous potential sources of error. Emissions from our own galaxy, for instance, can introduce patterns into temperature maps that might masquerade as genuine cosmic signals. To overcome this, astronomers observe the sky across multiple frequency bands, allowing them to separate the true signal of the cosmic microwave background from local foreground interference. Even so, after these corrections are applied, some unexplained features remain. A continuing debate centers on whether certain anomalies in the temperature data arise from subtle systematic issues in measurement or whether they truly point toward new physics. The Planck team devoted immense effort to refining their data processing, and independent groups have repeatedly reanalyzed the results in search of biases. Despite this scrutiny, the most puzzling trends, including the reduced power on large scales and the asymmetry between hemispheres of the sky, persist. This persistence suggests they are unlikely to be mere artifacts of observational error. Looking ahead, future missions promise to push this exploration further. Proposed satellites such as PICO aim to deliver another leap in resolution and sensitivity. Ground-based observatories, including the Simons Observatory, will also play a crucial role by focusing on specific frequency ranges to sharpen our understanding of cosmic microwave background fluctuations. Alongside these efforts runs an even more ambitious quest: the search for primordial gravitational waves. Unlike the gravitational waves already detected from merging black holes, which generate space-time ripples strong enough for current instruments to observe, primordial gravitational waves would be vastly weaker. If they exist, they would have been produced in the first fractions of a second after the Big Bang, stretching and compressing space itself. Detecting them requires not only exquisite precision, but fundamentally new observational strategies. As these ancient waves passed through the early universe, they would have left behind a subtle twisting pattern in the polarization of the cosmic microwave background. This so-called B-mode polarization is one of the primary targets of experiments seeking evidence of these primordial ripples in space-time. Unlike temperature fluctuations, which have been studied extensively, B-mode polarization is extraordinarily difficult to measure. It demands instruments of exceptional sensitivity, capable of teasing out an almost vanishing signal from a sea of cosmic noise. Ground-based telescopes, such as the South Pole Telescope and the Atacama Cosmology Telescope, are equipped with specialized detectors designed to scan the sky for these patterns. Their remote, high-altitude locations help minimize interference from Earth's atmosphere, which can otherwise distort microwave observations. Space-based missions offer another powerful approach. Agencies such as NASA and the European Space Agency have proposed next-generation satellites built specifically to pursue these measurements with unprecedented accuracy. Operating above the atmosphere, such instruments can obtain a cleaner and more precise view of the early universe. Another technique under consideration involves laser interferometry. However, primordial gravitational waves have wavelengths far longer than those detected so far, requiring interferometers on a truly unprecedented scale. The proposed laser interferometer space antenna mission envisions 3 spacecraft orbiting the Sun in a vast triangular formation millions of kilometers across. This configuration would allow the mission to detect ultra-low frequency gravitational waves inaccessible to ground-based detectors. While its primary goal is to study waves from supermassive black holes, it could also place new limits on the strength of primordial gravitational waves. Yet another innovative method relies on pulsar timing arrays. Pulsars are rapidly rotating neutron stars that emit beams of radio waves with astonishing regularity. By precisely monitoring the arrival times of these pulses across a network of pulsars spread throughout the galaxy, scientists can search for the faint, correlated disturbances that passing gravitational waves would produce. Astronomers can search for minute departures in timing that arise when gravitational waves drift past the Earth. Although pulsar timing arrays are especially well suited to sensing waves produced by merging black holes, under the right circumstances, they may also uncover traces of primordial gravitational waves. By observing pulsars over long periods with next-generation radio telescopes, such as a square-kilometer array, scientists could steadily enhance their sensitivity to these extremely faint signals. Different models of cosmic inflation forecast different strengths and spatial patterns for gravitational waves, so a confirmed detection could help identify which inflationary picture most accurately reflects the earliest moments of the universe. Some ideas even propose that failing to detect primordial gravitational waves above a certain threshold would effectively exclude standard inflation altogether, directing us toward alternative explanations for how the universe began. So far, the gravitational waves we have measured have originated from collisions between black holes or neutron stars, producing signals that align beautifully with the predictions of Einstein's general relativity. Yet many physicists suspect these waves may carry deeper information, subtle echoes of quantum processes that occurred at the dawn of time. One possible route for quantum effects to appear in gravitational waves lies in quantum fluctuations present in the early universe. Space itself was permeated by tiny, random variations in energy arising from quantum uncertainty. Under normal conditions, these fluctuations are far too small to observe, but during cosmic inflation, they were stretched across vast scales. Some of these amplified fluctuations may have generated ripples in space-time, forming gravitational waves marked by distinctive quantum signatures. If such signals exist, they would differ from the gravitational waves created by merging black holes or neutron stars. Conventional gravitational waves display smooth and predictable waveforms that follow the equations of general relativity. Quantum signatures, by contrast, could introduce minute distortions or irregular patterns within those waves, faint imprints that do not comfortably fit within classical physics. Certain theories even suggest that gravitational waves might carry entanglement, a curious quantum linkage in which two particles or even two regions of spacetime remain connected regardless of distance. Detecting these quantum features in gravitational waves would demand instruments far more sensitive than those we currently possess. Observatories such as LIGO and Virgo can already measure changes in spacetime thousands of times smaller than an atom. Yet quantum signatures would be subtler still, perhaps requiring entirely new detection techniques beyond today's laser interferometers. One promising strategy focuses on analyzing the statistical behavior of gravitational wave signals rather than examining individual waveforms alone. If quantum effects are present, they could subtly alter how waves are distributed over time or across many events. Some researchers have even suggested performing quantum experiments on Earth to mimic aspects of gravitational waves by creating controlled environments in which quantum particles interact with artificial gravitational fields. Such experiments would not replace observations from space, but they could offer guidance on what signatures to seek. Should quantum imprints in gravitational waves be confirmed, it would imply that gravity itself has a quantum character, challenging the long-standing divide between relativity and quantum mechanics, and potentially opening the path toward new theories of quantum gravity. In doing so, we might edge closer to grasping the true nature of space, space-time, and the origins of the universe. The theory of cosmic inflation accounts for why the universe appears so uniform on large scales, why distant regions share similar temperatures, and why space seems nearly flat rather than strongly curved. But what if inflation did not unfold exactly as we imagine? What if it took more complex forms that left behind subtle yet observable traces? One alternative is multi-field inflation, where instead of a single field driving the expansion, several interacting fields shaped its evolution. In such a picture, different fields could influence spacetime in distinct ways, producing gravitational waves that vary in strength or display unusual polarization patterns. Another idea involves intermittent inflation, in which the expansion did not occur in one smooth episode, but instead began, paused, and restarted through a sequence of phases. This start and stop behavior could imprint unexpected features on gravitational waves, introducing irregularities in their frequency or amplitude. Rather than a continuous spectrum of primordial waves, scientists might detect gaps, peaks, or other anomalies that standard models cannot easily explain. Some non-standard scenarios even propose that inflation was not purely an expansion. In certain models inspired by string theory and higher dimensional physics, the universe may have undergone a period of contraction before inflation commenced. In that case, the Big Bang would not represent an absolute beginning, but a transition from a contracting state into rapid expansion. The concept of warm inflation challenges yet another assumption. In the conventional view, inflation occurred in a cold and nearly empty vacuum, with particles appearing only after expansion slowed and energy was released. In warm inflation, however, the inflaton field continually interacted with other particles throughout the expansion itself. Even though present observations do not yet provide clear evidence for these non-standard forms of inflation, our ability to detect faint signals continues to advance, and the possibility that inflation was more intricate than we assume remains open. Future measurements may yet reveal how the universe's earliest moments shaped everything that followed. In the very first instance of the universe, matter and energy existed in an extreme state, unlike anything we see today. The cosmos was hot, dense, and expanding at a tremendous rate, experiencing profound changes in its fundamental structure. These events, known as cosmic phase transitions, marked moments when the properties of particles and forces shifted, much as water transforms into ice. As the temperature of the young universe fell, one of the most profound transformations in its history is believed to have taken place, a moment when the fundamental forces of nature parted ways. In the very first fraction of a second after the Big Bang, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force may all have been unified, manifestations of a single, deeper force. As the universe expanded and cooled, this unity began to fracture. The earliest of these changes would have seen gravity peel away from the others, followed by the separation of the strong nuclear force, and finally the division between the weak force and electromagnetism. These events were not gentle or continuous. They unfolded in sudden episodes, abrupt shifts, in which the structure of the universe changed almost instantaneously. Among the most fascinating of these transformations is the one associated with the Higgs field, the field responsible for giving particles their mass. In the early universe, the Higgs field likely existed in a very different state from the one we observe today. As cosmic temperatures dropped, the field transitioned into its current configuration, enabling particles such as electrons and quarks to acquire mass. If this change occurred suddenly, it may have sent powerful shock waves rippling through space-time itself. If instead it happened more slowly, it could have left behind relics, bubbles of distinct physical states that later merged. As these bubbles expanded and collided, they could have generated gravitational waves, faint echoes that might still be detectable in the universe today. Some theoretical ideas go even further, proposing that the universe may have begun in a state with more dimensions than we now experience, later transitioning into the four-dimensional space-time familiar to us. Others suggest that what we interpret as dark energy could itself be the outcome of a phase transition that has not yet fully completed. Future pulsar timing arrays, exquisitely sensitive to subtle distortions in space-time, may one day detect whispers from these early moments. Such observations could confirm whether these transitions unfolded as expected, or whether the early universe behaved in ways we have yet to imagine. Beyond changes in physical states lies an even deeper possibility, transitions not of phase, but of topology. Topology concerns how space is connected, its overall structure, rather than the objects within it. It addresses whether space stretches infinitely in all directions, loops back on itself, or conceals dimensions beyond our perception. Understanding how the universe's topology evolved at birth has become an increasingly compelling question. In the earliest instance after the Big Bang, Space itself may have undergone sudden topological shifts, altering not just what existed within it, but the very shape and connectivity of space. To grasp topology, it helps to think in terms of surfaces. A flat, infinite plane and the surface of a sphere can appear similar when examined locally, yet their global properties are profoundly different. A two-dimensional being traveling on a sphere would eventually return to its starting point if it kept moving in one direction. Our universe could be arranged in a similar way, finite yet without edges. In such a cosmos, a sufficiently long journey in a straight line might bring you back to where you began. If the universe changed from one topological state to another early in its history, it could have permanently reshaped space on the largest scales. One possibility is that the universe once possessed additional dimensions that later shrank or became hidden during its earliest moments. These dimensions may have curled up or collapsed, leaving only the three dimensions of space we experience today. Such a transformation would have influenced how matter and energy flowed through the young universe. Another idea is that the universe began with a far more intricate geometry, later smoothing into the structure we now observe. Rather than expanding from a single point, space may have been richly interconnected, with multiple routes leading to the same locations. If this were the case, the large-scale geometry of the universe might be far more subtle than it appears. Clues to such possibilities could lie in the distribution of galaxies across the cosmos. A topological transition might have guided the formation of galaxies, producing unexpected patterns, alignments, or symmetries. Future galaxy surveys, using increasingly powerful telescopes, may reveal whether such signatures exist. There is also the intriguing question of whether topological changes could still be occurring. If the connectivity of space can evolve, it suggests the universe may not yet be in its final state. Some theories propose that certain regions of space could still be undergoing minute topological shifts, driven by unknown physical processes. Though far beyond our current ability to detect directly, these changes could have profound long-term consequences for space-time itself. In this view, dark energy might be evidence that space is still subtly reshaping its fundamental form, implying that the universe remains a work in progress. The exploration of cosmic topology is still at an early stage, but as our observational tools grow more precise, we may begin to uncover the hidden architecture of the cosmos, revealing new insights into its earliest moments. Alongside this, another deeply strange idea has emerged: quantum entanglement on a cosmic scale. When two particles become entangled, measuring one instantaneously influences the other, regardless of the distance between them. This phenomenon has been demonstrated repeatedly in laboratories on Earth, where entangled particles appear to share information in ways that defy classical intuition. Although entanglement is usually confined to the realm of subatomic particles, some physicists are now asking whether it could extend far beyond the microscopic world, perhaps even shaping the universe itself. In this picture, galaxies, clusters, and vast cosmic filaments might be linked by hidden quantum connections, influencing their arrangement alongside gravity and dark matter. Shortly after the Big Bang, everything in the universe was compressed into an unimaginably small region. Quantum effects, which normally dominate only the tiniest scales, would have played a crucial role in setting the initial conditions of the cosmos. As the universe expanded, quantum fluctuations were stretched across enormous distances. Some theories suggest that these fluctuations carried entanglement with them, binding distant regions of space in ways that are extraordinarily difficult to observe today. The cosmic microwave background is remarkably uniform in temperature across the sky, a fact that is puzzling because light should not have had enough time to travel across the entire universe to equalize these regions. Cosmic inflation is the standard explanation, but if quantum entanglement connected different regions from the very beginning, it could offer an alternative account of this uniformity. Distant parts of the universe may have been linked long before light had the opportunity to travel between them. There are even proposals that dark energy itself may be connected to quantum entanglement on immense scales. If distant galaxies or entire cosmic structures are entangled, this hidden linkage could influence how space expands over time. In a similar vein, dark matter, which interacts gravitationally, but not through light, might be explained if some unseen form of entanglement affects how ordinary matter behaves on cosmic scales. Testing these ideas is exceptionally difficult, but they are not beyond the reach of science. By searching for patterns in the large-scale structure of the universe that cannot be explained by gravity alone, future observations may begin to reveal whether quantum connections truly span the cosmos. If quantum entanglement does play a part on the largest scales, it may give rise to faint but measurable correlations between galaxies and clusters, patterns that do not sit comfortably within our standard cosmological models. There is also a growing fascination with the possibility that black holes could be central actors in this cosmic entanglement. The holographic principle suggests that all the information contained within a black hole may be encoded on its outer boundary, rather like a hologram that captures three-dimensional information on a two-dimensional surface. Some researchers believe this concept might extend far beyond black holes, perhaps even to the entire universe itself, implying that everything we experience is linked through a deep, underlying web of entanglement. If this is the case, black holes could become natural laboratories for probing entanglement on scales vastly larger than those normally associated with the quantum world. While the notion of entanglement operating across cosmic distances remains speculative, it opens a strikingly new way of thinking about the profound connections that may exist within the universe. It prompts us to ask whether space itself is an emergent phenomenon arising from entangled information, rather than a backdrop that simply exists independently. Here, information theory begins to meet cosmology. Originally developed to understand communication systems, information theory has found unexpected relevance in our attempts to understand the universe, raising the possibility that reality itself is woven from information in much the same way a computer processes data. A central idea in this approach is that everything in the universe, from the smallest atoms to the largest galaxies, can be described in terms of bits of information. A bit is the most basic unit of information, representing a choice between two alternatives, like a coin landing on heads or tails. Some physicists have proposed that space-time, and perhaps even matter itself, could emerge from how these fundamental bits are arranged and processed. If that is true, the universe behaves less like a collection of solid objects and more like an immense computational system. The conventional picture tells us that the universe began with the Big Bang. Yet, if information lies at the heart of reality, the Big Bang may not have been a purely physical explosion, but a transformation in the structure of information itself. Some researchers have suggested that before the Big Bang, information existed in a different state, perhaps as a kind of quantum code that later unfolded into the universe we observe today. One of the most enduring puzzles in physics concerns what happens to information when objects fall into a black hole. Classical physics says that this information is lost forever, but quantum mechanics insists that information can never truly be destroyed. This contradiction led to the idea that black holes might store information on their surface, an idea known as the holographic principle. Some physicists have pushed this reasoning further, proposing that the entire universe could operate in a similar way. If so, the universe itself might function like a vast quantum computer, with the laws of physics acting as the rules that govern how information is processed. If reality is fundamentally informational, then time may not be a smooth, continuous flow. Instead, it could resemble a sequence of discrete steps, much like a computer performing one operation at a time. This perspective could help shed light on some of the mysteries of quantum mechanics, where particles can exist in multiple states simultaneously and appear to jump from one place to another without traversing the space between. Some researchers suggest that the structure of space itself may be a vast network of entanglement. If that is true, experiments designed to probe entanglement on large scales, including those involving high-energy cosmic rays, might reveal evidence that the universe is indeed an immense web of information. If the universe operates like a computer, then what is carrying out this cosmic computation? Is there a deeper layer of reality beyond the informational framework we perceive? Some scientists have speculated that if the universe is fundamentally computational, it might even be possible to create artificial universes through simulations, raising the extraordinary possibility that our own cosmos could be part of a larger structure. Despite how speculative these ideas may sound, the meeting point between information theory and cosmology is becoming an increasingly active area of research. The growing field of quantum gravity often relies on information-based principles to bridge the gap between general relativity and quantum mechanics. The idea that space-time itself emerges from entanglement, for example, is being explored as a way to explain how gravity operates at the smallest scales. The holographic principle offers a fresh way of thinking about cosmic origins. The term holographic comes from the concept of a hologram, a three-dimensional image encoded on a two-dimensional surface, which appears three-dimensional when illuminated. Applied to the cosmos, this principle took shape after physicist Stephen Hawking discovered in the 1970s that black holes emit radiation, leading to the famous information paradox. Classical physics suggested that anything falling into a black hole, including all information about it, would be lost to the universe. Quantum mechanics, however, forbids the destruction of information. The question then became, if black holes cannot destroy information, where does it go? In the 1990s, physicists such as Gerard T. Hooft and Leonard Susskind proposed that the information contained within a black hole could be stored on its event horizon. This idea implies that space and time themselves may not be the fundamental stage on which everything happens, but could emerge from a deeper and more basic level of reality. How could something as fundamental as the universe arise from information? What would it mean for our experience of space and time if they are merely a projection? The holographic principle offers a new perspective on the Big Bang. Rather than a singular, chaotic explosion that brought space and time into existence, the Big Bang may have been a phase transition. The origin of our universe may not have been the creation of space and time from nothing, but a shift in how information was processed, allowing the three-dimensional reality we experience to emerge from a two-dimensional field of information. If the universe is indeed a hologram, then it implies that everything we perceive, from the distant stars scattered across the night sky to the vast galaxies that populate the cosmos, is somehow encoded on a faraway surface. Every occurrence in the universe, from the birth of stars to the graceful motion of entire galaxies, could be understood as a projection emerging from this boundary. It hints that what we call reality may actually reside beyond the familiar dimensions of space and time that shape our daily experience. The holographic principle offers a possible bridge between general relativity and quantum mechanics by proposing that gravity, like all phenomena in the universe, emerges from a deeper structure rooted in information. In this picture, gravity is not a fundamental force, but a consequence of how information is stored and organized on the universe's boundary. Because this defining information is believed to be encoded on a distant surface, it is not immediately obvious how we might observe or interact with it directly. Yet recent developments in theoretical physics and cosmology are beginning to suggest ways we might search for signs of the holographic principle written into the fabric of the cosmos. Investigations into Hawking radiation and the quantum behavior of black holes may provide crucial clues as to whether this idea truly reflects reality. In particular, studies of quantum entanglement hint that the universe is connected in ways that transcend our conventional notions of space and time. Emergent gravity invites us to rethink the origin of the gravitational constant. Why does this mysterious number that governs gravity take the specific value it does? And why does gravity behave so differently from other forces, such as electromagnetism or the strong nuclear force? Questions like these have led some physicists to suggest that gravity may not be fundamental at all. Rather than existing independently of the universe's fabric, gravity could arise as a byproduct of more basic phenomena. These might include the behavior of quantum fields, the distribution of matter, or even the evolving dynamics of space-time itself. One of the earliest and most influential proposals for emergent gravity came from the physicist Eric Verlinde, who argued that gravity is not a fundamental force, but instead emerges from the way information is encoded within space-time. In his view, gravity behaves like an entropic force, arising from the tendency of entropy to increase. Gravity, then, reflects the statistical behavior of microscopic constituents rather than a fundamental interaction. When matter interacts, it creates an underlying information structure, and from this structure, gravitational effects naturally emerge. Verlinde's approach rests on the idea that space-time geometry is not fundamental, but a macroscopic description of deeper quantum processes. He draws an analogy with thermodynamics, where temperature and pressure arise from countless interactions between atoms and molecules. In much the same way, gravity resembles temperature, a large-scale phenomenon emerging from microscopic behavior. Within emergent gravity models, the gravitational constant, a central parameter in general relativity, may not be constant at all. Instead, it could vary depending on the quantum state of the universe. Some of the most intriguing support for emergent gravity comes from the way galaxies behave. Observations reveal that galaxies rotate in ways that defy the expectations of Newtonian gravity. According to conventional physics, stars in the outer regions of galaxies should orbit more slowly than those nearer the center, because there is not enough visible matter to provide the necessary gravitational pull. Yet this is not what we observe. The outer regions of galaxies rotate at roughly the same speed as their inner parts. The prevailing explanation introduces dark matter, an invisible halo surrounding galaxies that supplies the additional gravitational influence needed to account for these rotation curves. Emergent gravity, however, offers an alternative viewpoint. Verlinde suggests that the apparent missing mass may not be dark matter at all. Instead, the unexpected motion of stars in the outskirts of galaxies could reflect the emergent nature of gravity itself. If gravity is not a fundamental interaction, then dark matter may not be strictly necessary to explain these observations. The behavior of galaxies could arise from gravity acting in unfamiliar ways due to the underlying quantum structure of space-time. This perspective does not eliminate the possibility of dark matter, but it provides a new lens through which to examine galactic dynamics and the fundamental forces that govern the universe. In the standard model of physics, the gravitational constant, represented by the symbol g, is treated as a fixed value that determines the strength of gravity. In emergent gravity theories, however, g might change with cosmic conditions. Such variability could help explain long-standing puzzles, including the observed accelerated expansion of the universe. In some emergent gravity models, what we interpret as dark energy may also be an effect of gravity behaving in ways we do not yet fully understand. This approach offers a fresh perspective on cosmic evolution, particularly during the universe's earliest moments. Shortly after the Big Bang, the laws of physics were likely very different from those we observe today. Within an emergent gravity framework, gravitational behavior in the early universe may have developed gradually as quantum fields interacted and evolved. The forces we now regard as fundamental, gravity included, could have arisen from quantum fluctuations and interactions in the dense primordial environment of the early universe. If spacetime itself is not fundamental but emerges from deeper quantum processes, this could help explain the formation of large-scale cosmic structures, the cosmic microwave background, and even the nature of black holes. Rather than serving as a static stage on which cosmic events unfold, spacetime may be a dynamic, evolving entity shaped by quantum forces. The concept of emergent gravity remains in its formative stages. Theoretical physicists continue to explore its mathematical foundations, while observational cosmologists search the sky for evidence that might confirm or challenge these ideas. The distribution of galaxies and the intricate structure of the cosmic web may yet reveal clues about the true nature of gravity. These are questions that may one day be answered as we continue to push the boundaries of human understanding. Non-equilibrium dynamics in the early universe also play a crucial role in this story. Equilibrium is a familiar concept in everyday life, describing a state of balance where no significant changes occur unless disturbed. When ice cubes are placed into a warm drink, for instance, they melt until the temperature of the ice and the liquid equalizes. In the early universe, however, conditions were far from equilibrium, and it was within this restless, evolving environment that the fundamental features of the cosmos began to take shape. This offers an illustration of what equilibrium means on a cosmic scale. Equilibrium suggests a condition that is stable and unchanging, yet in the early universe nothing could have been further from that idea. Instead, The universe existed in a profoundly non-equilibrium state, one in which everything was evolving rapidly and physical processes were unfolding at astonishing speed. It is precisely this intense state of transformation that many scientists believe was fundamental to the emergence of the universe as we observe it today. Cosmological theories that explore non-equilibrium dynamics are not limited to the immediate aftermath of the Big Bang, but also address how the universe continued to evolve in its earliest moments, influencing everything from the formation of the very first particles to the birth of galaxies. In those initial instants after the Big Bang, there simply was not enough time or space for particles to settle into equilibrium, and so they interacted constantly, colliding and transforming without pause. The universe existed in a continuous state of flux, and it was this flux that decisively shaped the trajectory it would follow. Even after the period of inflation, the universe remained far from equilibrium. Shortly after inflation ended, the cosmos cooled sufficiently for particles such as quarks, gluons, and electrons to appear. Yet these particles did not emerge into a calm or orderly environment. They were still engaged in rapid interactions, decays, and collisions as space continued to expand and cool. As conditions changed, different phases of matter arose, each governed by its own distinctive non-equilibrium behavior. Of particular importance is the process of baryogenesis, believed to have taken place in the early universe, which was driven by these non-equilibrium conditions. This process produced an imbalance between matter and antimatter. In principle, the Big Bang should have generated equal quantities of both, which would have annihilated one another, leaving behind only radiation. Observations, however, reveal a universe composed almost entirely of matter, with antimatter being exceedingly rare. Such an imbalance could only have emerged under highly dynamic, out of equilibrium conditions, and the precise mechanisms responsible remain among the most profound unanswered questions in cosmology. As the early universe cooled, it passed through a series of distinct phases of matter, transitioning from a quark-gluon plasma to the formation of atoms. These phase changes were not slow or gradual. Instead, they occurred suddenly and dramatically, much like water freezing into ice. Each transition was driven by shifting conditions of temperature, density, and energy throughout the universe, all of which played critical roles in determining its evolution. For instance, during the period of nucleosynthesis, roughly 3 minutes after the Big Bang, protons and neutrons combined to form the first light elements, such as hydrogen, helium, and lithium. This was yet another moment in which non-equilibrium dynamics shaped the future of the cosmos. Rapid cooling, together with changes in the fundamental forces and particle interactions, made the formation of these elements possible and laid the groundwork for the later emergence of stars and galaxies. Another pivotal phase transition occurred when atoms began to form approximately 380,000 years after the Big Bang. Prior to this era, the universe was a hot, dense plasma filled with free electrons, protons, and photons, with no neutral atoms present. As expansion continued and temperatures fell, electrons and protons combined to form hydrogen atoms in a process known as recombination. This transition marked the moment when the universe became transparent to light, allowing photons to travel freely through space and giving rise to the cosmic microwave background. Since then, the universe has continued to exist far from equilibrium. Stars are born and die, galaxies collide, and new structures emerge, all while cosmic expansion carries on relentlessly. In many respects, the universe may never have reached a state of complete equilibrium. Looking ahead, we can only speculate about how ongoing expansion and the influence of dark energy might continue to drive an endless sequence of non-equilibrium processes. The universe may well exist in a perpetual state of transformation, constantly evolving, expanding, and rearranging itself. To explore these ideas, scientists have turned to advanced computational models that simulate the birth of the cosmos. At their heart, these simulations attempt to recreate the interactions among all the forces and particles present in the earliest moments of creation. They model how space expanded, how matter and energy behaved, and how the first structures began to emerge. The power of computational physics lies in its ability to translate abstract equations into vivid representations, making the hidden processes of cosmic birth more accessible. For decades, physicists have relied on the foundational frameworks of general relativity, quantum mechanics, and thermodynamics to understand the origins of the universe. Yet while these theories are extraordinarily successful, they were never intended to describe the extreme conditions that existed at the very beginning. Computational models help bridge this gap, using advanced algorithms and modern computing power to simulate scenarios that cannot be reproduced in any laboratory. These simulations provide a means to test hypotheses, visualize cosmic evolution, and probe the limits of current understanding. One area in which they are especially valuable is the study of inflation. Recreating inflation is far from straightforward, as the mathematics involved is deeply complex, and the conditions of the early universe were so extreme that even our most robust theories struggle to describe them fully. Here, simulations become indispensable. By adjusting parameters and exploring different assumptions, scientists can investigate a range of inflationary models, compare them with observational data, and uncover new possibilities for how the universe might have evolved. By incorporating quantum mechanics into these models, researchers can simulate fluctuations in energy density, interactions between matter, and the earliest stages of structure formation. This reveals how a universe that appears largely uniform on vast scales nevertheless contains regions of irregularity and complexity, including the clumping of matter that eventually formed galaxies. Developing these simulations demands the integration of multiple disciplines. It requires not only a deep grasp of physics, but also advanced expertise in computer science and mathematics to model such a complex, multi-scale system. Physicists often depend on sophisticated algorithms capable of processing enormous volumes of data. One widely used approach is the N-body simulation, which tracks the motion of large numbers of particles under the influence of gravity. These simulations can reproduce the behavior of galaxies, clusters of galaxies, and even larger structures, such as the cosmic web. Although they are commonly applied to later stages of cosmic evolution, the same principles can be adapted to study the early universe. When combined with simulations of inflation and quantum fluctuations, they offer a coherent picture of how matter and energy interacted in the universe's infancy. Despite their power, computational tools face substantial challenges. One of the greatest is the sheer scale of the problem. The universe is unimaginably vast, and simulating its birth requires tracking interactions among particles, fields, and energy densities across immense spans of space and time. Current simulations can either model small regions in great detail or examine large-scale cosmic features, such as galaxy formation or the behavior of dark matter. Simulating the entire universe down to the level of individual particles would demand computational resources far beyond what is currently available. As a result, scientists simplify their models, focusing on specific aspects of cosmic formation to gain insight without exceeding technological limits. Even so, these computational approaches have already yielded remarkable understanding of cosmic origins, clarifying how structures like galaxies and stars arise through the gravitational collapse of matter as revealed through simulation. We have also begun to see the universe from entirely new vantage points, especially when considering ideas such as cosmic inflation, dark matter, and dark energy. These concepts offer possible explanations that move beyond conventional thinking. By training artificial intelligence systems to detect patterns within enormous collections of data, or to forecast behavior inside highly complex models, scientists can dramatically accelerate simulations and uncover insights that would have been extremely difficult to reveal through traditional approaches alone. Machine learning techniques can be taught to identify faint, easily overlooked features in simulations that align with real-world observations, allowing researchers to concentrate their efforts on the theories that hold the greatest promise. In parallel, attention has increasingly turned toward the role of exotic matter in cosmic genesis. In recent years, a number of theories have explored forms of matter that extend beyond the standard model of particle physics, proposing that such unusual substances may have played a decisive role in shaping the universe we inhabit. In our everyday experience, Matter is built from atoms, themselves composed of protons, neutrons, and electrons. These components interact according to the well-established rules of the Standard Model, a framework that has underpinned particle physics for much of the past century. Yet despite its remarkable successes, this model has clear limitations, leaving many cosmic phenomena unexplained. To bridge these gaps, researchers have begun to investigate more exotic varieties of matter. Among the leading candidates for dark matter are hypothetical particles that fall outside the Standard Model. Particles such as weakly interacting massive particles or axions are thought to have been far more plentiful in the early universe than they are today, implying that they may have been crucial in shaping the formation of galaxies and clusters. Some theories suggest that dark matter particles emerged within the first moments after the Big Bang, possibly during a phase known as reheating. As the universe cooled, these particles could have settled into gravitational wells, clustering together and forming the underlying framework upon which galaxies were later built. If such particles were indeed abundant in the early universe, they may have acted as a form of cosmic glue, drawing ordinary matter together and enabling the emergence of the vast structures we now observe across the cosmos. Another intriguing line of inquiry focuses on exotic phases of matter that may have existed during the universe's earliest moments. Under extreme conditions of energy and density, matter behaves in ways entirely unlike those we encounter in daily life. The intense temperatures and pressures present just after the Big Bang could have produced unfamiliar phases of matter that do not persist under normal circumstances. One example is quark-gluon plasma, a state in which quarks and gluons, the fundamental constituents of protons and neutrons, are no longer confined within individual particles. Instead, they form an intensely hot and dense soup that may have filled the universe during the first few microseconds after the Big Bang. As this plasma cooled, it transitioned into the protons, neutrons, and electrons that later combined to form atoms. If this transition unfolded differently than current models predict, it could have altered the universe's fundamental properties, potentially influencing the formation of the first atoms or even the inflationary phase itself. Scientists continue to examine how these early states of matter may have influenced cosmic history and contributed to the universe's intricate structure. Some theories go further, proposing the existence of exotic particles present at the universe's birth, such as preons, which are hypothesized in certain models to be the building blocks of quarks and leptons. In these ideas, preons may have been the most fundamental constituents during the universe's earliest moments, giving rise to the forces and particles we observe today. Beyond this, there is speculation about entirely new forces of nature that could have governed the universe's early evolution. These forces may have operated alongside gravity, electromagnetism, the weak force, and the strong force. Theoretical models involving extra-dimensional spacetime suggest that such forces could have profoundly influenced how matter behaved and interacted during the universe's infancy. One particularly compelling idea proposes that the universe experienced a pre-Big Bang phase, during which exotic forms of matter existed prior to the event we traditionally identify as the beginning. During this pre-Big Bang era, exotic matter involving unfamiliar particles or interactions may have laid the foundations for the universe that followed. It has even been suggested that particles originating from higher dimensions or from quantum mechanical processes could have driven cosmic inflation itself, interacting with space-time to trigger the rapid expansion that set the stage for all subsequent structure. Within the domains of quantum mechanics and general relativity, matter and energy are deeply intertwined, captured by equations such as Einstein's famous relationship between mass and energy. Yet these formulations are rooted in our everyday understanding of matter and may fall short when describing the universe's earliest moments, when conditions lay far beyond anything we directly observe. If exotic forms of matter were involved, entirely new, theoretical frameworks may be required to explain how these substances behaved, interacted, and shaped the universe's evolution. This leads us naturally to questions of causality and the arrow of time, and to a re-examination of the universe's first moments. In daily life, we rely on clocks and calendars to track the steady passage of time. But before the universe began, or during the earliest instance of the Big Bang, Was time itself a meaningful concept at all? The classical view derived from general relativity holds that time began with the Big Bang, that both the universe and time itself emerged together in that moment. Yet as we probe deeper into cosmology and quantum theory, this simple picture begins to blur. Causality lies at the heart of how we understand reality. It tells us that every effect has a cause, forming a continuous chain from one moment to the next. However, when examining the origins of the universe, some theorists argue that our conventional notion of cause and effect may no longer apply. Causality is closely linked to the arrow of time, the idea that time flows in a single direction from past to present to future. This arrow shapes our experience of the world, yet it remains one of the most debated concepts in modern physics. For centuries, we have assumed that the universe began with a singular event, the Big Bang, marking the start of both time and causality. Today, cosmologists are increasingly open to the possibility that the arrow of time we experience is not a fundamental feature of reality itself, but rather an emergent property of the universe's large-scale evolution. At the quantum level, reality behaves in profoundly unfamiliar ways. Particles can occupy multiple states simultaneously, become entangled across immense distances, and at times appear to violate our intuitive notions of causality altogether. If quantum mechanics lay behind the creation of the universe, then time and causality at the very beginning may have behaved in ways fundamentally unlike anything we experience today. It is possible that events did not unfold through a clear sequence of cause and effect, or even that time, as we understand it, simply did not apply. One idea, known as the block universe model, suggests that time itself is an illusion, and that every event, past, present, and future, exists simultaneously within a single cosmic structure. In this view, rather than a flowing chain of causes and consequences, the entire history of the universe is already laid out, every moment fixed in place. That would mean the universe and all that happens within it were effectively set from the very beginning, and our sense of time moving forward is merely an internal perspective within this vast structure. Inside the event horizon of a black hole, the familiar behavior of space and time is thought to become so distorted that it loses all resemblance to everyday experience. If time can behave in such extreme and unfamiliar ways at the edge of a black hole, it raises a profound question. Could something similar have occurred in the earliest moments of the universe, just after the Big Bang? Perhaps the birth of the cosmos involved a breakdown of ordinary causality, where time was not a simple straight line progressing from past to future. Some theories of quantum gravity suggest that quantum fluctuations in space-time itself may have produced tiny, unpredictable jumps or bounces in the fabric of the universe. Rather than unfolding smoothly and continuously, the early universe may have passed through chaotic, non-linear transitions that defy our classical notions of cause and effect. Clues to these processes may still be visible today. Patterns observed in the cosmic microwave background, including subtle temperature variations and polarization features, could be remnants of quantum mechanical activity during the universe's earliest moments. If these fluctuations were shaped by quantum processes, they may have been influenced by events that challenge our traditional understanding of causality. Phenomena such as quantum entanglement or other non-local effects could, in principle, have affected how the universe evolved, linking events in ways that do not fit neatly into a cause-then-effect framework. To explore these ideas, future cosmological observatories will push the limits of what we can detect as we attempt to unravel the story of the universe's birth. The next generation of instruments, some already under development and others still years or even decades away, promises to bring us closer than ever to the edge of understanding. From sensing the faintest gravitational waves to probing the very first instance of cosmic formation, these missions will expand the boundaries of knowledge and allow us to look further back into the past than ever before. The James Webb Space Telescope, while primarily designed to study distant galaxies and stars, has already begun to transform our view of the early universe through its infrared capabilities. Its sensitivity to infrared light allows it to see through cosmic dust and observe objects that are far too faint or distant for previous telescopes. This includes the potential discovery of the first galaxies formed after the Big Bang and even glimpses of star and planetary system formation in the distant past. The telescope is built to investigate the universe's earliest eras, including the cosmic dawn, when the first starlight emerged. Through this, it will help reveal the processes that shaped the young universe and explain how galaxies and other large-scale structures began to form. Beyond this telescope, several ambitious missions are in preparation, each offering new ways to explore the universe's history. One of the most exciting is the Laser Interferometer Space Antenna, scheduled for launch in the 2030s. This mission will use 3 spacecraft arranged in a triangular formation, each linked by lasers capable of detecting the faintest ripples in space-time. Positioned millions of kilometers apart, the spacecraft will measure incredibly small changes in their separation caused by passing gravitational waves with extraordinary precision. This approach will allow the detection of waves with much longer wavelengths than those accessible to ground-based observatories, opening an entirely new chapter in gravitational wave astronomy. Another major project is the Square Kilometre Array, a vast radio telescope to be constructed across South Africa and Australia. When completed, it will be the largest and most powerful radio telescope ever built, offering unprecedented detail in our view of the cosmos. One of its central goals is to map the large-scale structure of the universe with extraordinary accuracy, tracing how galaxies and clusters have evolved over cosmic time. By examining the distribution of galaxies and the cosmic web they form, scientists will gain deeper insight into the forces driving the universe's growth and expansion. Measuring distances between galaxies with exceptional precision will also shed light on the influence of dark energy on cosmic expansion. Through its radio observations, the array will provide a new window into the universe's infancy and the forces that guided its evolution. These observatories will be complemented by other groundbreaking missions that explore the cosmos in different ways. The upcoming Euclid mission from the European Space Agency is designed to probe the nature of dark energy and dark matter by constructing detailed 3-dimensional maps of the universe. By studying how light from distant galaxies is bent and distorted by dark matter, the mission will help reveal the properties of these elusive components and clarify their role in cosmic expansion. To search for primordial gravitational waves, scientists are also developing highly specialized instruments and observing strategies. One such proposal is the Cosmic Explorer, a ground-based observatory intended to detect low-frequency gravitational waves, particularly those originating in the universe's earliest moments. With its advanced sensitivity, it could provide transformative data about how the cosmos formed. Alongside this, the Event Horizon Telescope, a global network of radio telescopes, continues to refine our view of black holes. Having already produced the first image of a black hole in 2019, future versions of this array may deliver even more detailed observations of supermassive black holes, especially those residing at the centers of distant galaxies. These observations may open entirely new windows onto the nature of gravity, space-time, and the physics of the most extreme environments imaginable. As our understanding of the universe grows ever deeper, a striking and unsettling idea has come into focus, one that sits at the boundary between empirical science and philosophy. It is the possibility that the entire cosmos, everything we observe and experience, could itself be a simulation. This proposal, brought into the scientific mainstream by the philosopher Nick Bostrom in 2003 through what became known as the simulation hypothesis, suggests that sufficiently advanced civilizations might one day develop the technology to simulate whole universes, complete with consistent physical laws, a detailed history, and even conscious beings capable of self-awareness. Within this framework, what we perceive as reality may be nothing more than an extraordinarily sophisticated computational construct, potentially indistinguishable from what we would call the real world in every meaningful sense. The idea of a simulated universe forces us to question some of our deepest assumptions about existence, reality, and our position within the cosmic story. While it sounds like something lifted from science fiction, it has nonetheless been taken seriously by a number of respected scientists and philosophers. Some physicists have even suggested that, in principle, there could be observable signs, subtle clues embedded in nature itself, that might lend support to this extraordinary hypothesis. At the heart of the simulation hypothesis lies a deceptively simple question. How do we know that the universe we observe is the fundamental one? Our experience of reality is mediated entirely through our senses, which are known to be fallible, and through instruments such as telescopes and detectors, which only ever provide indirect information. If advanced civilizations were capable of constructing simulations of staggering complexity, could we ever truly rule out the possibility that we are living inside one? This question poses a profound challenge to scientists who seek to understand the very foundations of reality itself. One promising avenue of investigation involves searching for inconsistencies, imperfections, or glitches in the fabric of the universe. If our cosmos were a simulation, it might not be perfectly seamless. There could be signs that it is not fundamentally real in the deepest sense. This mirrors how we identify flaws in computer simulations here on Earth, such as those used in climate modeling or video games, where limits in resolution or processing power can reveal themselves. If the universe operates like a computational system, there might be faint but detectable patterns, irregularities, or constraints in physical laws that hint at an artificial construction. Some researchers have pointed to the concept of quantum discreteness as a potential clue. In quantum mechanics, space and time appear not to be smooth and continuous, but granular at the smallest scales. Rather than an unbroken continuum, the universe may be built from tiny, indivisible units, much like pixels on a digital screen. If this discreteness is a fundamental feature of reality, it could be interpreted as evidence of an underlying informational structure where the laws of physics are implemented in discrete steps. There is speculation that future experiments might be able to probe this graininess of space-time itself, potentially exposing the hidden architecture beneath the universe we observe. Another intriguing possibility lies in the values of the cosmic constants, the numbers that determine the strength of gravity, the speed of light, and the behavior of the fundamental forces. These constants appear to be finely tuned in a way that allows complex structures and life to exist. Some have wondered whether this apparent fine-tuning could be the signature of deliberate design within a simulated universe. In this view, the creators of such a simulation would choose parameters that produce a stable and coherent cosmos, much as an engineer defines the rules of a virtual environment. The constants we measure might then be the result of intentional choices rather than cosmic coincidence. Despite the fascination of these ideas, it is crucial to acknowledge that there is currently no direct evidence supporting the simulation hypothesis, and many scientists remain deeply skeptical. The concept itself raises difficult questions about what we even mean by reality, and whether asking if the universe is real is a meaningful question at all. Some philosophers argue that even if our universe were a simulation, it would still be real in every sense that matters to us. Our experiences, our thoughts, and our lives would retain their significance, even if their ultimate origin were computational. From this perspective, the simulation hypothesis becomes less about proving or disproving reality, and more about reshaping how we think about existence itself. If our universe was simulated, it would imply the existence of higher intelligences responsible for its creation and operation. Such beings would possess technologies far beyond anything we currently understand, perhaps even the ability to manipulate the fundamental laws of physics themselves. This raises unsettling questions. Could these intelligences be aware of us? Might they observe our actions, analyze our behavior, or interact with us in ways entirely beyond our comprehension? The idea stretches the imagination, yet follows logically from the premise. If an advanced civilization could create a simulated universe, what might that imply about the origins of our own cosmos? Could the Big Bang represent the initialization of a simulated reality, set in motion by an intelligence whose motives we may never fully grasp? Such speculation has been invoked as a way to think about enduring mysteries in cosmology, including the fine-tuning of physical laws and the apparent randomness inherent in quantum events. It also forces us to confront the increasingly blurred boundary between physical reality and digital or virtual realms, questions that are central not only to cosmology but also to the future of artificial intelligence and technology. Several experimental ideas have been proposed to search for signature errors in the cosmic microwave background. If the universe were a simulation, certain anomalies or repeating patterns might appear, analogous to graphical artifacts or glitches in a computer-generated environment. Although such experiments remain highly speculative and are still in their infancy, they represent a bold and unconventional approach to probing the deepest nature of reality. As our technological capabilities advance and our own simulations grow ever more sophisticated, it is conceivable that we may one day gain partial answers to these questions. Until then, the notion that our universe could be a vast cosmic experiment conducted by an advanced intelligence remains one of the most provocative and mysterious ideas in modern science. Now consider another concept that challenges our intuition just as profoundly: the idea of entropy in reverse, and the possibility of a universe that could rewind its own history. The second law of thermodynamics, a cornerstone of modern physics, tells us that in a closed system, entropy, a measure of disorder, must always increase over time. From the moment of the Big Bang, the universe has been evolving in a particular direction, toward greater disorder, randomness, and decay. Stars exhaust their fuel, energy spreads out, and structures gradually lose their organization as time moves forward. Yet within theoretical physics, there exist speculative ideas that question whether this progression is truly absolute. Some theories entertain the possibility that under certain conditions, entropy could decrease, allowing the universe, at least locally or temporarily, to reverse its apparent direction of time. At first glance, this seems deeply counterintuitive. Our everyday experience of time is relentlessly one-directional. We grow older, causes precede effects, and events occur only once. But what if, at a fundamental level, the universe allowed for moments in which this order could be undone? Exploring this question leads us into some of the most mind-bending regions of modern physics, involving ideas such as time reversal symmetry, closed time-like curves, and the nature of causality itself. One potential mechanism for entropy reversal lies in the nature of time at very small scales. Some theories suggest that in the quantum realm, the laws of physics may be largely indifferent to the direction of time. If time can run both ways at the level of fundamental particles, then, under highly unusual conditions, it is conceivable that larger structures could briefly reflect this reversibility, allowing the universe to partially rewind itself, reversing the march of entropy, if only for an instant. The rise of entropy, and the idea of entropy itself when examined more closely, can be understood as the way energy spreads through a system. As energy becomes more uniformly distributed, entropy grows. In systems that are highly ordered, entropy remains low. The gradual movement toward higher entropy mirrors the universe's intrinsic tendency to drift toward equilibrium, a state in which everything is distributed as evenly as it can be. Yet, if the universe were somehow to undergo a reversal of this process, energy could once again become concentrated, potentially giving rise to a state of lower entropy. One speculative framework that explores this notion is known as the Boltzmann brane scenario. This idea suggests that in the distant future, as the universe continues to expand and entropy keeps increasing, fluctuations within quantum fields could momentarily reduce entropy in small, isolated regions of space. In principle, such fluctuations might create brief islands of order, perhaps even something as complex as a functioning brain, complete with memories, though disconnected from any broader physical context. The purpose of this thought experiment is to illustrate that if entropy can fluctuate downward in tiny regions, then a local and fleeting reversal of entropy might be possible. Although this remains firmly theoretical, it implies that entropy may not always progress along a perfectly smooth or predictable path, and that, on rare occasions, it could temporarily decrease. Beyond these isolated possibilities, another way to imagine a reversal of entropy lies in the concept of the Big Crunch. The Big Crunch represents a potential ultimate fate of the universe, in which the expansion that began with the Big Bang eventually halts and reverses, allowing gravity to pull everything back inward. In this scenario, the universe would contract toward a singularity, resembling the extremely dense state that existed before the Big Bang itself. As the cosmos shrinks, entropy could, in principle, run backward, with matter and energy becoming increasingly concentrated. While current observations indicate that the universe's expansion is accelerating due to dark energy, the Big Crunch remains a valuable theoretical model, one that envisions the universe dramatically retracing its history on the largest possible scale. If such a collapse were to occur, it would suggest that the growth of entropy is not inevitably one-directional, and that reversal is at least mathematically conceivable. Another fascinating dimension of this discussion involves closed time-like curves, solutions to Einstein's equations of general relativity that permit the existence of loops in time. Put simply, a closed time-like curve is a path through space-time that bends back on itself, forming a loop in which events could, in theory, repeat. Within such loops, an occurrence might happen, and then, by virtue of the curve's structure, happen again, potentially allowing for a local reversal of entropy. If a region of spacetime were to contain such a curve, the flow of time itself could appear to reverse within that confined area. This immediately raises profound paradoxes, such as the well-known grandfather paradox, in which traveling back in time could alter events in a way that prevents the traveler's own existence. These contradictions underscore the immense difficulty of reconciling time reversal with fundamental physical principles, particularly causality, the idea that causes must come before effects. Despite these conceptual challenges, closed time-like curves are taken seriously by some physicists. Certain solutions to the equations of general relativity, including those describing rotating black holes known as Kerr black holes, predict the presence of such curves. These mathematical results imply that time travel, or a reversal of time's arrow, could be possible under extraordinarily extreme conditions. Although such conditions lie far beyond any current or foreseeable technology, they remain consistent within the mathematics. If time itself can curve and twist in these extraordinary ways, then entropy might follow, with energy and matter temporarily settling into states of lower disorder. At the quantum level, the picture becomes even more subtle. Quantum mechanics describes particles as governed by probabilities rather than strict determinism. This opens the door to the idea that, on very small scales, entropy might behave differently, allowing for localized decreases in disorder. Quantum entanglement, in particular, suggests that information can be linked across space in ways that challenge classical intuitions about how it flows. While entanglement does not directly imply time reversal, it does stretch our conventional understanding of causality and may hint at processes that are not rigidly bound to the familiar arrow of time. This leads naturally to deeper questions. Could the Big Bang itself have been a low entropy state emerging from an earlier phase of greater disorder, perhaps as part of a cyclical cosmic pattern? Might the universe one day rewind itself, with entropy decreasing before a new era of expansion begins? Could fluctuations in quantum fields or the dynamics of black holes permit localized rewinding of time? These ideas remain speculative, yet by exploring the possibility that entropy might, under certain conditions, reverse, we are compelled to reconsider our assumptions about time, causality, and the evolution of the universe. As scientific inquiry continues to probe these possibilities, it becomes increasingly clear that the cosmos may be far more intricate and enigmatic than we have ever imagined, with implications that push the limits of human understanding and continue to inspire curiosity and exploration.